So the likelihood that you will be hit or your local area will be hit is actually pretty low. Although there is an interesting case that occurred in 1954 in Alabama. And this is the only modern day documented story, I guess I should say, of someone actually being struck by a meteorite. Her name was Elizabeth Hodges, and she was asleep on her couch in her living room, and a meteorite crashed through her roof. Apparently it bounced or ricocheted off of a radio and struck her kind of in the hip, or kind of along the side of her leg right here. And this is her and her doctor right here. All right, so she wasn't permanently injured. This meteorite was about 7 inches long, and it just kind of scraped against her hip right there. It's again, no broken skin or anything, but just a great big nasty looking bruise. And then of course she survived. She's one of the few people, well, one of the only people that we know of really to be actually struck by a meteorite. So talk about very low probabilities of things happening, but there you go. There's somebody who happened to be in the wrong place at the wrong time. All right, so this is interesting. This kind of shows the relationship between, first of all, size of objects, whether they're asteroids or comets or meteors, and their explosive power when they strike the Earth or explode in the atmosphere, and also the likelihood of them happening. So the vertical axis right here is, you might say, the interval between events in years. All right, so this is 1/10 of a year. Every, whatever power this is right here, every 1/10 of a year, you're likely to have something like that happen. And that's why this right here, upper atmosphere explosions, occur about once per month. We don't hear too much about them. And the good news is that they don't have very much power. All right. They're also not very big at all, maybe 10 meters. Okay, so they don't affect all that much of the world. But as we go down, we see the intervals getting bigger and bigger and bigger, once every 10 years, every 100 years, 1,000, 10,000, etc. And these events pretty much follow a straight line as we go down. As they increase in diameter, they decrease in likelihood, but they do also increase in power. That is, explosive power in megatons, MT, of TNT. In fact, megatons is the unit that we use to measure the explosive power of nuclear devices. So the atomic bombs that were dropped on Japan at the end of World War II were right about, I think they were right about in here. I think they were in a couple kilotons, not even a megaton. Mega means million, kilo means 1,000. So if you're talking about megatons, so this is 1 megaton right here. That is 1 million tons of TNT exploding, which is quite a bit. And that just about lines up with, well, a little bit less than that, is Chelyabinsk in 2013. This affected thousands of people, all right? Tunguska in 1908, that right there is just about a megaton of TNT. Many, many, many times greater than the explosive power of the atomic bombs dropped from Japan. As we move downwards, they become less likely and less frequent, but they become bigger and more obvious, and also having more of an impact on Earth as we know it. Barringer Meteor Crater, you might recall, is simply, we just call it Meteor Crater. That's the one that's in Arizona that you can go see right now. There's a very deeply buried crater under the Chesapeake Bay that we think happened 35.5 million years ago. Now you're talking about, what's that, between 1 and 10 million megatons, so a million millions. That's, is that in the trillions, I guess? Trillions of tons? These numbers are getting so big that we can't even imagine them. And then, of course, there's Chicxulub. This is the one that we think killed off the dinosaurs 65 million years ago. That's the one that's off the Yucatan Peninsula. So as the diameter of the object goes up, the explosive power of the object goes up. But thankfully, as this graph shows us, the likelihood of it happening goes down and down and down. What's also kind of interesting is that with big impacts, since they affect a large number of people, on average, you actually have a fairly high likelihood of being affected or killed by an asteroid or a meteor. 0.01% to 0.1% likelihood of you being killed by an impact. Now compare that against being in a car accident. All right, 0.008%. not very likely. Car accidents happen all the time, but there are millions and millions and millions of people in cars all the time that don't get in an accident. So that's a pretty small percentage. Drowning, 0.001%. So that's not very likely either. But if you take impacts, which affect a large number of people, even though they aren't very likely, if you take the average likelihood of somebody being killed by an impact, it's actually a relatively high likelihood of that actually happening to you. Not that you should lose sleep over it. The likelihood of it happening is not very likely or not very high, but it does affect a lot of people when it does happen. So that's how we can sort of play with numbers and take averages and say that, oh, well, on average, you're going to have a more high likelihood. Either way, it's not very likely at all. Events and deaths are very rare, which is good news for us. So what can we do to minimize the impact hazard? Well, we can watch for these things. We have a couple of different agencies which do that. There's one called Space Watch, all right, which what that does is that monitors objects with a diameter of over 100 meters in diameter. So that's about the width or the length or size of a football field, a long ways. And these are only objects that have orbits that cross Earth's orbit. All right, if they cross Earth's path at any time, whether the Earth is there or not, we keep an eye on it. All right, and we've got about 85,000 of these objects crossing Earth's orbit that we know of. There's also another agency called NEAT, Near Earth Asteroid Tracking. So any object that is about 1 kilometer in diameter, we identify those as well. It may or may not pass or cross over Earth's orbit, but if it's nearby, that's something we keep a track of. So that's certainly bigger than a football field. And we have official government agencies. We also have amateurs, people that are just good citizens using telescopes and digital imaging devices to discover things. Some comets, some meteors, some asteroids actually have been discovered by regular civilians that don't have any scientific training, but just like doing this kind of thing and are into it and just want to be able to contribute to the greater good. But the good news is most of these objects that threaten Earth or that are in that have the likelihood of possibly crossing Earth's orbit, that really are not going to collide with Earth at all. Here's an asteroid called Ida. This kind of gives you an idea of how big they are. This probably is massive enough for you to be able to stand on it and be pulled down to it because of gravity. You'll notice right here you have all these craters. All right. Well, these craters are because of impacts from other asteroids, other small objects hitting it. And you'll notice that each of these craters has kind of an upraised rim right here. Well, that's ejected, that's thrown out. And so it's thrown out, and it kind of gets pulled back down by Ida's gravity, which is why it kind of settles around the rim right there. So these are big enough to have their own gravity. And if you look at the scale is pretty telling as well. So if this is 10 kilometers right here, it's the whole length of it, 10, 20, 30, 40, maybe 50 kilometers. All right, that might be the distance from, say Downingtown right here to Philadelphia right there, or maybe a little bit less. All right, but that gives you some sense of how big that is. So maybe one of these craters could hold an entire town like Downingtown or Westchester. So that gives you a scale. So if this object were to enter Earth's atmosphere, it would definitely have a major impact on us. Okay, so what if one of these objects is on a collision course with Earth and it is only a matter of time before it enters Earth's atmosphere and creates all kinds of catastrophe and chaos? What are our options? Well, if you've seen the movie Armageddon, the whole movie was about that very thing. This asteroid about to strike Earth, about to wipe out civilization as we know it, and us sending a crack team of scientists up in the space shuttle to actually blow it up. Yes, you heard that correctly, blow it up. Supposedly in the movie, it was to blow it into 2 pieces so it would split and go around the Earth. But there's a lot of problems with that movie, and it's just kind of for fun. It's not really a scientific movie at all. But the problem with blowing it up is that you have, instead of one giant thing, you've got millions or billions or trillions of small pieces now that could become possible asteroids and rain down on Earth. Not only that, but they could be radioactive as well. In order to blow it up with an explosion big enough, you'd probably need some sort of a nuclear or thermonuclear bomb. Right? Well, all those asteroid pieces will now be radioactive. So it's not just a matter of will it hit you, but will it even come near you and spread radiation all over the place. So that may not be a likely solution to the asteroid threat. Nudging it out of Earth's orbit is a possibility. Actually, as I recall, in that movie Armageddon, I think at one point that was actually an option as well. They had to, something didn't work right, and they had to go to Plan B. So they wanted to nudge it, and they had to blow it up, or vice versa. But they did consider the possibility of nudging it out of Earth's orbit too, and that actually would be probably more likely to have some sort of good effect. Remember, in space there is no friction, and so if you have some sort of a jet or propulsion means, if you give it enough time to nudge it out of Earth's orbit, it really would not take all that much power to do that. Space, you could move an entire planet by nudging it very, very gently over time. And if that's the case, you could certainly do that with an asteroid or a comet as well. But the thing is, we would certainly need time to study the object and to be able to make preparations to be able to do that. If the object is small enough and it is going to hit a certain area that will be affected, but not the whole Earth, that is, you could possibly evacuate as well. All right, so if we detect an object that we have no means of avoiding and it's going to strike Earth, we can figure out, using physics, exactly where it's going to land and where it's going to enter the Earth's atmosphere. So if it's small enough, it's going to affect that local area. Let's evacuate people so that they won't be affected by the impact. We do have a scale called the Torino impact scale that basically evaluates the risk, the measure of risk that certain near-Earth objects pose to us. Something that's a 0 on the scale is really no hazard at all. All right, something that'll burn up in the atmosphere, and things like this happen thousands of times per day. We've got thousands of meteorites or meteors burning up in the Earth's atmosphere. They don't get a chance to become meteorites because they don't touch the ground. So that'd be a hazard of 0. Something with a normal hazard scale risk would be like a close encounter or pass near Earth, but it has an unlikely probability of striking the Earth. Something that's a 3, 4, 5, we say merits attention by astronomers. That means it's worth looking at. This is actually what was happening when the Chelyabinsk meteor or comet took place in 2013. Astronomers were actually watching something else that was a possible threat that wasn't all that threatening, but it caused them to miss the Chelyabinsk Airburst. Something that's threatening, 6, 7, or 8. You may have a close encounter with Earth, or a very close encounter with Earth, maybe between the Earth and the Moon. That's actually happened in recent years. Or even a collision. If a collision is imminent, that would be a 6 or 7 or 8. If there is a collision, maybe you might just have localized destruction or possibly even a tsunami. But if you've got certain collisions, and that is a 9 or a 10, you have high levels of devastation, maybe regional devastation, or even, devastation that threatens civilization as we know it. All right, so this is the Torino impact scale right here, and it really, it isn't a measure of the risk, but it's a measure of how threatening is an object that we actually have already identified. Okay, so to wrap things up, let's go back and revisit the Chelyabinsk meteor and look at the 5 fundamental concepts of mitigating disasters like this. First of all, a couple facts about it. It was the largest known asteroid since Tunguska, and we completely missed it. We were looking the other way. All right, it was a fireball. The fire, as it were, was produced by the friction with the atmosphere. It was moving at several times the speed of sound. All right, and so as a result, moving through the air compressed and created all kinds of shock waves and massive amounts of heat, simply because of the friction of it moving through the atmosphere. So when it did explode, and many times these meteors have like frozen gases like water or methane in them. All right, because of the heat, if those gases vaporize, you can have a huge explosion, and so that the shock wave going out in all directions can produce a lot of damage. Like this, like broken glass. All right, if you're in office buildings, or I don't know, this looks like colored glass, could even be stained glass. This is a result of the Chelyabinsk Airburst, and if that shock wave goes out in all directions, it's going to affect basically every piece of glass that is facing outside in a certain area. We actually did find parts of this meteorite. It went through a lake, or a frozen lake, and so they identified where it was by seeing this hole that it created. They found a fragment, divers found a fragment at the bottom of the lake quite some time later, and we found that this object was about 3.6 times the density of water, so pretty dense, probably metallic in composition. All right, so the total weight of it, depending on the airburst, the amount of energy that was released, was estimated to be about 11,000 tons. So pretty good size. Where it blew up was important. Now, it did injure a lot of people, but if it was closer to the ground, it would have become absolutely catastrophic. It was near a fairly urban area, but it wasn't over a really, really urban area. And if it were closer to the ground and over a really populated area like, say, Moscow or St. Petersburg, you could have millions of deaths occurring. Not just because of flying glass, but because of the shock wave and ensuing fireball as well. So here's a little piece of the meteor right here. It's very dark, very almost iron-looking. And here's the lake and the hole in the lake that was, or the hole in the ice that was created by this impact. So could Chelyabinsk have been avoided? Well, possibly. Remember, the scientists were looking at another near-Earth asteroid, one that was a little bit less risk, and so maybe if they had been spreading out their watchful eyes into the skies, they could have caught it. But it was just kind of one of those coincidental things. But it wasn't terribly large. All right, and these small objects are just difficult to find, difficult to see in space. They are small, and also they don't reflect all that much light, which is really what helps us to see them. Again, I mentioned there is a larger meteor that scientists were actually looking at. So the ability to determine if these things are going to strike the Earth is really dependent upon how good is our, you might say, how detailed can we look at the heavens. All right, and so. Greater as technology increases, we can build bigger ground-based telescopes and be able to track these things, but they require funds. So we can appropriate more funds to observing NEOs, or that is near-Earth objects. That's what it stands for. So as technology improves, we'll be able to see more and more of these. We're tracking a lot of them, but there's always going to be a few that kind of slip through the cracks. So. Just to kind of wrap this up right here, this will give you an idea of how big this object was. So here's the space shuttle right here. All right, you've seen the space shuttle. Actually, I saw it in person a couple of weeks ago. This is the Chelyabinsk Meteor, or about 18 meters end to end, which isn't all that terribly large. All right, so the objects were tracking this other thing, this Asteroid 2012 DA-14, going by the Earth, and look, it was in between the orbit of the Moon and the Earth, so that was something to actually watch, so they weren't just kind of wasting their time. This was certainly something of a threat, but it kept moving. But Chelyabinsk came in from the opposite direction towards the sun, which also could have been a problem as well. Because if you look towards the sun, it's hard to identify things, and this is where it actually struck right there. So, that is our chapter on impacts and extinctions. If you have any questions, please make sure you come see me. But in the meantime, thanks for watching, and I'll see you on the next one.